All right, now let's move on to the second part of our lab that will be mainly focused on a different modality, on different data modality, primarily it's vision. So in the first part of the lab, you learn how to build a general transformer and also apply it for machine translation. Here we will be working on some practical applications of vision. We will learn how to incorporate and use transformer for basically on images. The structure of our second part would be very similar to what you saw on the first part. So we will discuss basically what kind of libraries we use, the data set, tokenization, model architecture, training, and testing. And the primary goal is to learn how we can apply transformers to classify images. All right, so the first one, the part about libraries is very general. We basically load pretty much similar libraries you guys saw during our labs. So let's move on and discuss the dataset. For our dataset, we will be using MNIST dataset, which is basically written digits. And the goal and our task for this second part of the lab is to teach the model how to classify, basically how to detect image specific digits. So for example, here would be digit 0, it's handwritten, and the model should learn how to associate this image with a 0. And the same for the 8 and all other images. We could see that basically we have different quality of handwriting. Sometimes it's very easy compared like to some other special cases. It might be a little hard to identify which particular digit is written. As you remember from all previous homeworks, from a particular homework 2, that if you're dealing with particular images or videos, the first choice would be always CNNs. So we will try to learn and we'll try to build a CNN model that will be able to scan our images and learn how to associate with a particular label. Here, we will be trying to use a different approach. So as you remember, when transformers came up to the picture, it was with attention is all you need paper, everyone was trying to use transformer for all possible tasks because they were thinking and they were saying, oh, it's a general architecture that could be applied for so many different data modalities and everything. And researchers struggled a lot, particularly with vision, because even though they could apply transformers, it didn't converge. They had different scaling issues and everything. And the primarily reason why it was happening, like, and one of the reasons why it was happening is with data preprocessing. Because the most important part is we have to decide what are we doing with how do we feed our data, our images to the transformer. As you remember with language, we take a sentence and we tokenize it. We break it into words. And here we need to do something similar. We need to come up with a smart way. What should we do with this image to make sure the transformer performs really well? And the paper, which was a vision transformer VIT in 2020, they came up with this really interesting idea, which is they basically take an image and they break it into small patches of sub images that they later they feed into transformer. And it's very similar how we also work with language, as I said, like we have a sentence and we break it into words. Could be characters, could be couple of words or anything. Here we do a similar thing. We take an image, we break it like into uniform and similar patches of data, and this data would be used to train the model. Um, all right, so here's the function called Apacheify. We use this function that will help us to create these small patches of data. So as you can see, we slice the image to create these patches of small images. Then we append it to the list, and then we stack them. And so this function helps us to get into any image we have and break it into equal sizes boxes. This is the main part. So like the main part is we learn how like we take in image data and we make sure it's suitable for our transformer. And then once we've done this, we can easily move on and work with the transformer. As you learned in the previous lecture, during the lecture and also previous lab, there are different models. Could be models that only use encoder part, other models would be just decoder based, or it could be encoder and decoder. For the vision transformer, we're only using the encoder part. So let's look at the scheme. So we take an image, we break the image into small pieces. Typically, in the original papers, they're using 16 by 16 pixels. And so then we put them all together. Then for us, it's important to think about, like, first it's important to know, like, what's in the image, but also the position. So like we could move them back. That's why they also use position embedding, which help us to identify mm, from which place a particular patch to which place a particular patch belongs. And so once we have the patches combined with positional encoding, we can feed in into a transformer encoder, which is a very classic architecture. And since our task is to classify what's on the image, we add the classic MLP and the classification layer. All right, now let's see in code how it works. So step one, we need to write a function for positional embeddings. And this is a very classic one. You also saw it in the previous part, the part one of the lab. We basically, what we need to do is for each patch, we need to come up with a positional encoding, which is using, and depending on the index of the patch, odd or even, we will have a using different formula. Um, so this is positional encoding. Next, we need to come up with a function class for the multi-head attention. This class is exactly the same that you saw in the part one of the lab. Let's look at the forward function. So usually if we want to check what's in the class, it's important to, like, it's easier to check what's in the forward. So as you see, the forward function is pretty much the same as you saw previously. So we have queries, keys, and values. Then we do our attention. Then we apply a mask if we want, like if we want to do a mask. Then we do a softmax, and then we multiply it finally by our values, and we map them and return the results. So it's very classic. You've seen it multiple times. And so this is a building blocks. And now we are moving on to also add like one more thing. We need to write a function for add a norm and feed forward. In lab one, in part one of the lab, this was separate classes. Here we combine into one. So let's look at the forward. So all we do in the forward function, we call, first of all, we apply norm to our inputs, which is basically embedded positional encoded inputs from images. Then we apply multi-head self-attention. Then we add residual connection. Then we do one more norm and move it through MLPs, and then one more residual connection. This is our block. This is basically our encoder block. And so finally, we build everything together. So this is the final function, which is vision transformer encoder. Here we combine the entire flow. So first, we take the shape of our image. We create small patches of from this image. We linearly map them and add the classification token. Then we also add positional encoding. And so this step is very useful because now we moved from images, just like single images, to small patches of images that also contain positional embeddings. And then all we do, we just like add the transformer blocks. We can add them as much as possible, with as many as we want. And transformer blocks is basically encoders. And once we've done this, we extract the classification, basically the label. Run through the MLPs and learn how to go to the output space. So this is our function. This is our class. And once we did this, we can move on to the training and testing. So for the training, we define some simple hyperparameters. We train for 5 epochs. We identify the learn rate, patch size, number of patches, which is like how many patches per image we have, number of blocks, which is number of encoder blocks. Then also we do identify hidden dimensions within the transformer block, number of heads for our attention, and the output dimensions, basically number of classes. We print up a model. You can see it's super small, just 1,000 parameters, but that's okay, which is for training. Okay, and then we have our summary. And finally, we train our model. This is a very simplified version. We train the model. we print the epoch and the loss, we see it converges. So basically, the loss decreasing, which is great. And finally, once we got this, we can move on to a testing, which is also very straightforward. We can see our test loss and test accuracy. So our accuracy is 76%, which is pretty good. And as always, we really want to see what's actually our model predicted. So we can basically basically plot the results. So for example, image one, we want to predict 7, and the model predicted 7. Sometimes model made mistakes. So for example, here we wanted to predict 2, but the model predicted 8. Or for example, here we wanted to predict 5, but the model predicted 6. But honestly, this was a very complicated case, so I think it makes sense. It's like sometimes it's the handwriting is really bad, so even people won't be able to distinguish. So it's pretty good results. So with this, it's basically it about this model. Let's move on to the architecture again. Look at this again, and yeah. So with this, we learned one more data modality, which is vision. And the most important part about any transformer is like what do we do with our data? How do we feed the data in our model? And the main advantage and breakthrough of this particular paper is that they come up with this interesting idea to create patches of data and feed in, which also partially help them to use, not to use any CNNs at all. They just get away with the transformer and perform really well. And this architecture provides state-of-the-art performance. All right, so feel free to try this notebook. Hopefully, it will be helpful for you doing homework for. But also, if you're working on any related tasks for your projects, feel free to look at it as well. All right, thank you so much. Bye.